Good morning, grade 9 students. Today we will start with a new chapter, chapter 13, Equilibrium of a Body. At the beginning, you have to prepare a notebook and a pen in order to write some notes, and don't forget to follow these instructions. At the end of this chapter, you will be able to
Why does a swimmer push the water backward? Oh no, there's a hole in the boat. Don't worry, do as I say. Jump in the water and push the water backward with your hands. This will help you to move forward towards the shore. No, you are not pushing the water backward. See, you are moving forward towards the shore. Do you know why you were able to move forward by pushing the water backward? To understand this, you need to learn about Newton's third law of motion.
Hooray!
Newton's third law of motion states that, for every action, there is an equal and opposite reaction. When we swim, we apply force and push the water backward with the help of our hands. This is action. In response to this action, the water pushes us forward with an equal force. This is reaction. Thus, in order to move forward and swim, the swimmer pushes the water backward.
So the first point to be covered is about the principle of interaction. As you have seen, forces exist in pairs. For every action, there is a corresponding reaction. This principle was stated by Newton in his third law, and which states the following. If an object A exerts a force on object B, we can express it in this way, where A is the producer of the force and B is the receiver, then B will exert a force or a reaction on A, such that these two forces have the same line of action, opposite directions, and same magnitudes. If we check these two writings, you can notice that objects A and B are switching their roles. So in case they ask you to state the principle of interaction, you can write this part. So if you please, you have to memorize it. And since we are talking about two forces which have specific relation, it's time to learn about two types of relations. The first one is called a vector relation, and the second one is called a magnitude relation. For better understanding, let's take an example of interaction. In this figure, you can see a foot which is exerting a force on the floor. This force is expressed by this yellow vector or these yellow vectors, and in return, the floor is responding. The floor is reacting by a force on the foot represented by these blue vectors. To write the forces of interaction, let's say that the foot exerts a force on the floor. We're represented by a force vector F. Foot is the producer, floor is the receiver. Then the floor exerts a force on the foot. These two forces are called forces of interaction between the floor and the foot. So in case they ask you to write down the names of the forces of interaction, we have to pay attention for the two objects which are interacting and make use of their names to write the name of the forces of interaction. These two forces have the same line of action. Let's, for example, take into consideration this one. These two forces, they act along the same oblique line of action. They have the same magnitude. Check the length of each vector, and we're using the same scale just to express the fact that they have the same magnitudes. And concerning their directions, you can see that they have opposite directions. In order to express such relation, we can write a vector relation as follows. If we add these two forces, since they are opposite in direction and they have the same magnitude, then they cancel each other in a way we get 0 vector. The resultant is 0. This relation is called vector relation between these two forces of interaction. Don't forget to put the vector in this relation. We can also express it in this way. These are two forces of interaction. They have equal magnitudes but opposite direction. Don't forget this minus just to show the opposite direction. And concerning the other type of relation is the magnitude relation. We are talking only about one characteristic. So since they have the same magnitude, we can simply write it in this way. Here we shouldn't put a vector and there is no minus. We're not talking about direction. We are only talking about magnitudes. Let's have a look at some real-life examples of interaction. For example, this man will exert a force on the ball, and the ball exerts a force on him, so he moves backward. Another tricky example right here. Here we have an interaction between the hammer and the glass. First trial and the second trial. In the first trial, the hammer goes back. Just wait, and now it moves backward. If you want to write the names of the forces of interaction between the hammer and the glass, we can say that the hammer exerts a force on the glass, H for the hammer and G for the glass. So the glass exerts a force on the hammer, switching roles. But concerning the second trial, right now, we can say that the glass is broken. The hammer exerts a force on the glass, and the glass exerts a force on the hammer. But because of the breaking in the glass, you can think that the hammer is exerting a force stronger than that exerted by the glass on the hammer. Is this right? No, it's wrong, because according to the principle of interaction, the forces of interaction have the same magnitude. So don't be tricked. We can explain the breaking of glass by the fact that the force exerted by the hammer on the glass was enough to break the glass. But the force exerted by the glass on the hammer, which is of the same magnitude, is not enough to break the metallic part of the hammer.
Here it's a simple experiment to prove that the magnitudes of the action and reaction are equal. Here we have two spring balances that can measure 10 Newton each. If we pull it from one side, then the spring balance will read 2 Newton. But also the second one read the same magnitude, which is also 2 Newton. If I pull the second one, here the spring balance is reading 5 Newton, but also the second one reads the same number, 5 Newton. This proves that the magnitudes of the action and reaction are equal.
And now let's take one more example about interaction. Here we have a book and the earth. The first point to think about is the forces of interaction happening between the book and the earth. Pause the video and try to list them. We have a force exerted by the earth on the book, represented by F vector earth on book, and here's the force represented by this vector, and at the same time the book exerts a force on the earth. Now it's time to write the vector relation between these two forces. They have the same magnitude but opposite direction. And this is the magnitude relation between these two forces. They have equal magnitudes. Here we have no vectors. According to this example and the previous one, we can say that interaction could be of two types. We have the interaction by contact, just like the one happening between the hammer and the nail, or between this ball and the tennis racket. Interaction could also happen from a distance, just like the one happening between these two magnets and these two charged balls. Now it's time to make application. Let's read the given. We have two positively charged balls, A and B, and because they have the same charge, they repel each other as shown in the adjacent figure. Pay attention that the size of ball A is bigger than that of ball B. The first question is to name the forces of interaction that exists between A and B. Make use of these two names so we can say that there is a force exerted by A on B and the force exerted by B on A. These are the forces of interaction. Now you have to give the vector and magnitude relation of these two forces. Here is the vector relation, and you can also write it in the other way. You can add these two forces to get zero vector. And here is the magnitude relation. Now you have to characterize these forces. Just pause the video and write the characteristics of these two forces. Concerning the line of action, the two forces of interaction act along the same line, which is horizontal in this case. Concerning the magnitude, because they are forces of interaction, they have the same magnitude, so it's the same for both. Concerning the point of application, and since we're talking about forces of interaction that act from distance, then it's the center of gravity. If we are talking about the force done by A on B, so it is applied at the center of gravity of ball B. And when we talk about the force exerted by B on A, so this force is applied at the center of gravity of ball A. Concerning the direction, they have opposite direction. The force exerted by A on B, because we have repulsion, so B is repelled to the right, and the force exerted by B on A to the left. The final question, you have to choose the correct representation of the forces, knowing that the same scale is used. Pause the video and think about the answer. Yes, the correct representation is B, because the two forces have the same magnitude, and because we're using the same scale, so the length of these two vectors should be the same. Don't be tricked by the big size of A. So you assume that A is exerting bigger or higher or stronger force, so the vector should be longer. This is false. And the right figure is figure B. As a summary, we can say that when body A acts on body B by a mechanical action characterized by a force Fa on B, B will react by a force B on A. The action and the reaction are opposite. Here is the vector relation, equal but opposite in direction. These two forces of interaction could be contact forces or acting from a distance. Don't forget that the forces of interaction have the same magnitude, the same line of action, but opposite directions. Thank you for your attention.